Okay, good afternoon, class. Welcome back to the final training for Chemistry Olympiad. Today, we'll be tackling the final set of notes, which is on alkenes, set number 9. So in the previous sessions, we have done introduction to organic chem. We know that organic chemistry is about the study of molecules containing the element carbon. All right. We know that organic molecules are obtained by fractional distillation of crude oil. All right. And we have studied the homologous series of alkanes in the previous session. So we have alkanes and now we have alkenes. So there are some critical differences between alkanes and alkenes. So let's take a look at the critical differences. So firstly, I've summarized everything you need to know about alkenes on the first page. Now, alkenes have a general formula of CnH2n. So you immediately realize that, oh, there's no plus 2. It's just 2n. So meaning the number of hydrogen is double the number of carbon. That's how you tell whether something is an alkene or not from its formula. Hydrogen is double of carbon. Okay, double of the number of carbon. So for example, something like C8H16. This tells you it's an alkene because the hydrogen is double the number of carbon. Next, the functional group is the carbon-carbon double bond. And because the carbon-carbon double bond is present, we say it's unsaturated. So you need to know that double bond between carbon atoms present means the hydrocarbon is described as unsaturated. Okay? Next, we have the physical trends. Okay, the physical trends are the standard physical trends that you have already learned under alkanes. Flammability decreases as the number of carbon increases. Viscosity increases, melting and boiling points increase. All right, and we'll look at some of the chemical reactions, as well as for my Sec 4 students, we're going to look deeper at the mechanism behind the reaction. So moving quickly on to page 2. Now, page 2 is just a quick summary of how to name and how to draw an alkene. So I'll just quickly fill it in. Now, this homologous series is called alkenes. Alkenes have a general formula of CnH2n. So as mentioned, the number of hydrogen is double the number of carbon. The functional group is the carbon-carbon double bond. All right, so alkenes are described as unsaturated hydrocarbons. So there are two words here, unsaturated and hydrocarbons. So why are alkenes unsaturated hydrocarbons? Firstly, we should say that they are organic compounds containing hydrogen and carbon only. All right, so this is the part about hydrocarbons. Hydrocarbons means they are organic compounds that only contain hydrogen and carbon atoms. And importantly, why are they unsaturated? Because they contain or they have one carbon double bond. Now, unsaturated means it has at least one carbon double bond. At least one. All right. Okay. So even if it has more than one carbon double bond, it's still considered unsaturated. But for alkenes, alkenes only have one double bond. Okay. So now we move on to the table. Immediately you realize the naming has a certain system. So I hope you remember the system is the prefix tells you the number of carbon atoms. So the prefix, the first part of the name tells you the number of carbon. Immediately you realize the first member has 2 carbon atoms. Ethene. Ethene, 2 carbon, C2H4. And it goes in order. Propene is 3, butene is 4 carbon, pent, hex, hept, oct. So this is the order, all right, of prefixes. Eth is 2 carbons, prop is 3 carbons, and so on and so forth. All right. Now, using the general formula, you are quickly able to write the molecular formula because N represents the number of carbon atoms. All right. So that's quick to write. Okay. So I believe you can quickly fill in the molecular formula of the alkenes. Now, importantly, after you fill in the molecular formula, you realize that there's a pattern. Between every single member, you will add a CH2 group. All right. Basically, to go from C2H4 to C3H6, you add a CH2 group. Okay, and so on and so forth. Now, when it comes to drawing, I think it's not very difficult. I think you can quickly draw it. Now, the key thing to take note of is whenever you draw any organic molecule, you should always write down the functional group first. So the functional group of an alkene is a carbon-carbon double bond. So you should always include that first. Following that, you should ensure that every carbon atom in your organic molecule has 4 bonds. So if you draw ethene, ethene has 2 carbons. The 2 carbons are linked by a carbon-carbon double bond because that's the functional group for alkenes. Then you make sure that the carbon has 4 bonds. So please ensure that you draw 4 lines around each carbon. And please bear in mind that a double bond counts as 2 bonds already. Next, propene. Now, propene has 3 carbon atoms, right? Only 1 double bond is present. Remember, alkenes only have 1 double bond. The other one is a single bond. All right, only 1 double bond, the other one is a single bond. Then you make sure that every single carbon has 4 bonds. So please count carefully. And finally, the one in the middle, the carbon in the middle, there is 1 bond here, 2 bond, 3 bonds. So there's already 3 bonds. So you really only have 1 more hydrogen. All right, so try not to make any careless mistakes. This is propene. Finally, the last one is butene. Now, butene, I'm sure my Sec 4 students already know what I'm going to say next. Immediately, to draw butene is not difficult. Okay, 4 carbons in a row, 1 double bond. The rest, just make sure that every carbon atom has 4 bonds around itself. Now, this is butene. But is this the only way to draw butene? All right. So I think the Sec 4 students have gone through this with me. Why must the double bond be at the end? Why can't we have chosen the double bond to be in the middle? Isn't this equally valid? The functional group doesn't need to be right at the end, right? It could have been somewhere in the middle, and indeed that's so. That is the case. This is totally possible. All right. So this is another way to draw butene, the 4-carbon alkene. However, these 2 molecules are not the same. These are called isomers of each other. The first one on the left-hand side is called but-1-ene. But-1-ene means the double bond is at the end. The 1 indicates the double bond is at the end. Okay, when you see but-1-ene, it means the double bond is right at the end. This one on the left-hand side, on the right-hand side, sorry, it's called but-2-ene. All right, so the 2 in this case means the double bond starts or is located at the 2nd carbon atom. All right. And these 2 are called isomers of each other. Okay, so just a recap. Isomers are organic molecules with the same molecular formula, but different structural formula. Okay, so what it means in this case is that both the molecules I have drawn, but-1-ene and but-2-ene, all right, they have a molecular formula of C4H8, but the way, the structure of the molecule is slightly different in the sense that the carbon-carbon double bond, one of it is at the end, one of it is in the middle. All right, so the structure is slightly different. Okay, so now we move from structure, drawing, and naming to the trends in physical properties, which I will quickly run through. All right. Okay, I also don't want to end too late. I want to go to the chemical reactions of alkenes. All right. So once you have copied this down, can you please give me a thumbs up so that I know I can move on to this? All right, so let's move on to the trends in the physical properties. Now, the trends in the physical properties actually, right, if you just studied alkanes, the previous set of notes, you would have also gotten the same trends for alkenes. So for alkenes, the trends in physical properties like viscosity, flammability, melting and boiling points, the trends are the same as that for alkanes, which is what? So we look viscosity. As the number of carbon atoms increases, the viscosity also increases. Now, what is viscosity? Viscosity is how sticky a substance is. So as the number of carbon atoms increases, the molecular size and mass increases, the alkenes become more viscous, more sticky. All right. In terms of flammability, you will realize that as the number of carbon atoms increase, the alkene becomes bigger and bigger, the flammability decreases. Okay, the larger alkenes are less flammable, they are more difficult to burn. They don't burn very well, so they produce more soot and smoke when they burn. Finally, all right, why does flammability decrease? Now, the larger alkenes contain a larger number of carbon atoms. Okay, now for my Sec 4 students, this is a new term. Actually, we can say that the CH ratio is higher. The carbon to hydrogen ratio is higher. It's the same as saying there's a larger number of carbon atoms. All right. Now, because the CH ratio is higher, they will require more oxygen in order for complete combustion to take place. When you have more carbon atoms, you will need a larger number of oxygen molecules for complete combustion. The problem is air only has a certain fixed amount of oxygen gas. So if you need more oxygen, it's quite likely that there's insufficient oxygen in the air for you. Right? So if it needs more oxygen, but air can only supply this amount of oxygen, therefore, it wouldn't burn so well. All right? It is more likely that these alkenes, which are larger, will undergo what we call incomplete combustion. All right? Okay, moving on to the next page. Now, next page is the trends in the melting and boiling points. So I've given you the melting and boiling points of the alkenes. Okay, it's a matter of filling up the table. So I'm just going to quickly fill up the table for you with the formula. All right, so this is the formula for the alkenes. Now you can quickly work out the state at room temperature. So remember, room temperature refers to 25 degrees Celsius. So at 25 degrees Celsius, are these alkenes gases, liquids, or solids? So we can quickly work this out given the melting and boiling points. Okay, so remember, you have learned how to use a number line to work out what state these substances will be given the melting and boiling points. So ethene is a gas, propene is also a gas, butene, also a gas. Then we go to pentene. Now, pentene is a liquid. All right. At 25 degrees Celsius, pentene is a liquid. Hexene, also a liquid. Heptene, also a liquid. Finally, octene, also a liquid. All right. So what can you see from this trend in the boiling points as well as the melting points? As the number of carbon atoms increases, the melting and boiling points both generally increase. And that's why the larger alkenes tend to be liquids or solids, whereas the smaller alkenes tend to be gases. All right. So why is this the case? Why do the melting and boiling points generally increase? This is because as the number of carbon atoms increases, the molecular size and mass of the alkenes also increase. Okay, so as you have more and more carbon, the molecular size as well as the molecular mass, how heavy the alkenes are, will also increase. Therefore, the intermolecular forces of attraction between the alkene molecules become stronger and more extensive. So the weak intermolecular forces of attraction are dependent on the molecular mass. If the molecules have a higher mass, generally the weak intermolecular forces of attraction become slightly stronger, more extensive as well. All right, so more energy is needed to overcome the weak intermolecular forces of attraction in larger alkenes. Oops. Okay, give me a minute. Okay. Okay, so this part is about physical properties and that ends the physical properties. Now the next part is about how do you obtain alkenes, which is on cracking. All right, so before I go on to the next part, can I just check the physical properties for those in the Zoom meeting? Are they okay? Do you have any questions to ask? If it's okay and you have finished copying, just also give me a thumbs up so that I know that you are done with it. Okay, now some of these physical trends, okay, please learn. All right, learn the trends in physical properties. It will help you as well for the Sec 3s when you get the Sec 4 Pure Chem next year. All right, for my Sec 4 students, I sincerely hope this is a good revision for you. You may need it later on as well when you are doing all the practice papers that you are given. All right, now the next page really highlights how do we obtain small alkenes. Now, alkanes and alkenes can be obtained by fractional distillation of crude oil. But the keyword here is how do you obtain small alkenes? Smaller alkenes are obtained by cracking. All right, so this is listed as a revision because we actually saw this in set number 7, Introduction to Organic Chem. So let's just quickly go through cracking. I hope you realize now, cracking is necessary. What is cracking? Cracking is a process of converting larger hydrocarbons to smaller hydrocarbons, right? Cracking is the process to convert larger hydrocarbons to smaller hydrocarbons. How would you describe cracking? Oh, it requires this catalyst, this temperature. All right. Now, what is the importance or the significance or the uses of cracking? Cracking is useful because the demand for smaller hydrocarbons is higher. So we need cracking to meet the demand for smaller hydrocarbons, which is higher. Okay. Now, cracking produces smaller alkanes and alkenes. That's how you get smaller alkenes. Okay. Just a quick revision on cracking. Now let's move to the main bulk of today, which is the chemical reactions of alkenes, which is combustion and addition. Now, alkenes are reactive. Alkenes are reactive generally because they contain a carbon-carbon double bond. Now, a double bond may not look like a lot to you, but a double bond means there are more electrons there. Because if you think about it, how is a double bond formed? A double bond is formed when the carbon atoms share two valence electrons with each other, right? So when you drew the dot and cross diagram, you would have drawn this, 1 dot 1 cross, 1 dot 1 cross, right? So it tells you that, okay, in a double bond, there will be two pairs of shared electrons. So we can say that the double bond creates a region of high electron density. High electron density just means there are more electrons in that particular place. So whenever you see a carbon-carbon double bond, we generally consider it to be a region of high electron density. Because it's a region of high electron density, it attracts things which are electron deficient. So we call them electron deficient species or electrophiles. So the word phile here means like. Things that like electrons. Things that like electrons are things that lack electrons, right? Electron deficient species want to get electrons. All right. So there are two basic types of chemical reactions of alkenes. Okay, can we correct this? Typo error is alkenes. Chemical reactions of alkenes. Okay, so we already know that, okay, alkenes are reactive because they contain a double bond between carbon atoms. This is a region of high electron density, which attracts electron deficient species like electrophiles. All right. Now, for my Sec 4 students, you will realize that this is greater depth than your alkenes notes. Because your alkenes notes, I didn't talk about electrophiles. Okay, but this is Chemistry Olympiad, so there's actually greater depth in this. Okay, so now we move on to the first type of reaction, which is combustion. Now, combustion, similar to combustion of alkanes. Combustion of alkenes, there are two types: combustion, complete combustion, incomplete combustion. Complete combustion is where oxygen is in excess. It's very plentiful. The only two products of complete combustion is CO2 and H2O, carbon dioxide and water. Incomplete combustion is when oxygen is limiting. Now, when oxygen is limiting, all right, incomplete combustion occurs, and the products are CO, carbon monoxide, soot, and water, H2O. Okay? So you must be comfortable with writing the equations for complete combustion. So we can quickly do it. Okay, so you must be able to balance this. How do you balance this? Carbon is balanced with CO2. So C2H4 must have two CO2, two carbons. Hydrogens are balanced with water. 4 hydrogens on the left, so 2 H2O on the right. Why 2 H2O? Because 2 times 2 gives you 4 hydrogens. 2 times 2 gives you 4 hydrogens. The last step is to combine the oxygen. How many oxygen atoms do you have in total? 2 times 2 is 4. 2 times 1, 2. So 4 plus 2, 6. So you need 3 oxygens. Okay, so C2H4 plus 3O2 forms 2 CO2 we have propene C3H6. All right, I think I'm back. Sorry, my connectivity dropped for a while. All right. So as mentioned, right, why is there a 2 in front of C3H6? It's because I know that I need to multiply a 2 throughout, all right? So that when you have 2 C3H6, you have 6 CO2. Okay, you also have 6 H2O. And therefore, you will have a total of 9 O2. All right. So these are the chemical equations, the balanced chemical equations for complete combustion. Okay. Now we're going to move on to addition reactions, and that's where we will spend most of the rest of the session today. All right. So all the reactions you're going to see next are all addition reactions. Okay. Now addition is a special type of reaction which you must be familiar with, not just in O levels, but if you are planning to do more chemistry later on in poly, in university, as well as for Chemistry Olympiad, you must be familiar with what addition reactions are. So let's move on to addition reactions. Now, I've just shown you basically what an addition reaction is. You realize that there's a double bond involved. It involves a carbon-carbon double bond, right? Then you have something that adds to the double bond. Importantly, the double bond is gone. At the end, the double bond is gone. Double bond is now a single bond at the end, and the two atoms have added to the carbon atoms in the double bond. All right, to form a single product. So now let's synthesize all this. What is an addition reaction? An addition reaction is a reaction where a group of atoms add across a carbon-carbon double bond to form a single product. Okay, it doesn't form multiple products. You don't have like one molecule plus another molecule on the right-hand side. On the right-hand side, there really is only one thing formed. That is the telltale sign that is an addition reaction. When you look on the right-hand side of the equation, has only one product. That's how you tell that it is an addition reaction. All right. So all the following reactions I'll be teaching you involving alkenes are all addition reactions. All right. So what can you add to an alkene? Well, you can add many things. You can add hydrogen. So that's the first reaction you see below. Addition of hydrogen to alkenes. This is called hydrogenation. Now, hydrogenation requires a temperature of 200 degrees Celsius, and the catalyst used is nickel. Nickel metal is the catalyst used as a catalyst for the hydrogenation of alkenes. Now, why nickel? So for the Sec 3s, you have just done periodic table with Miss Ng in class. Nickel is an example of a transition metal. It's one of those metals found in the middle of the periodic table. So nickel and its compounds are typical catalysts. All right, so nickel happens to be the catalyst for hydrogenation. All right. So what do you notice? When the hydrogen adds to the carbon-carbon double bond, the double bond is gone, right? It went from ethene to ethane, alkene to alkane. So if you wanted to convert alkenes to alkanes, you add hydrogen at 200 degrees Celsius in the presence of nickel catalyst. All right. Now, alkenes are unsaturated. Alkanes are saturated. So this is a good way to convert an unsaturated substance into a saturated one by adding hydrogen. This is called hydrogenation. Okay, and the conditions are 200 degrees Celsius, nickel catalyst. Now the checkpoint, okay, I'll just quickly draw the answer for you. Basically, you focus on a double bond. Look where is the double bond. Then you basically break that double bond into a single bond. So at first it's a double bond, now it's a single bond. And then you just need to add 2 hydrogens to it. Okay, the rest of the molecule will remain the same. So you went from propene to propane. All right. The second one, double bond is in the middle. Again, break the double bond, become a single bond. Stick your 2 atoms onto different carbon atoms, okay? So you can see it adds across the double bond. All right, so you went from butene to butane. Okay. Now, I hope you realize that hydrogenation is used to make margarine from vegetable oil. Now, I will not go through the next page because I will just tell you that hydrogenation is used to make margarine from vegetable oil. So this reaction to add hydrogen to an alkene is useful because it's what's used to make margarine. This is the margarine that you can spread onto your bread, okay, when you eat breakfast, for example. Okay, now moving quickly on to addition reaction 2, which is on page 9 instead. Okay, I'll skip the part about polyunsaturated as well. All right, so let's go to page 9 in the interest of time. Now, the alkenes can also be reacted with bromine. We can add bromine across the double bond. Crucially, you realize the bromines are not together anymore. They are added to different carbon atoms. And this is always the case in an addition reaction. Whenever you add something across the double bond, the 2 atoms must be added to different carbon atoms. So the 2 bromine atoms are spread out across different carbon atoms. All right. So this is crucial. Is added to different carbon atoms in the carbon-carbon double bond. Okay. So the bromines are never ever on the same carbon atom if it's an addition reaction. Okay, so with that in mind, it's easy to draw the final answer. Again, focus on where the double bond is, break the double bond. So the double bond was in the center, now you break it to form a single bond. You attach the bromine. Remember what I just said, the bromine is always on different carbon atoms in the double bond. So the 2 bromines are never on the same carbon. And then you just have to fill up the rest. The rest of the molecule you realize actually didn't react. Okay, and that is the final structural formula of the product formed when bromine water is added to the following alkene. All right. Okay. Now, this reaction by adding aqueous bromine is actually very, very useful because this is how you can distinguish and differentiate between alkanes and alkenes. All right. Alkenes will react with bromine, aqueous bromine. So it will decolorize reddish brown aqueous bromine from reddish brown to colorless. All right. Whereas alkanes don't react this way with bromine because alkanes do not have a carbon-carbon double bond. So there's no color change observed with the alkane. All right, Ken? So this is a useful distinguishing test for alkanes and alkenes. This is how you can differentiate alkanes and alkenes. Okay. So with that, okay, can I just check that this reaction is done? It's okay for you? Okay. Now, the next part I'm moving on to will be new for both the Sec 4 and the Sec 3s. The next part is A level, right? Now, how do these addition reactions occur? The mechanism behind the addition reaction is called electrophilic addition. So remember just now I said something about electrophile. Okay, electrophile. What is the meaning of electrophilic addition? Electrophilic means electrophile. Remember, electrophile means something that is electron deficient. What is electron deficient? Something that is positive or partial positive will be considered electron deficient. If it's partial positive, it's electron deficient, it wants electrons. If it wants electrons, where can it go to find it? Where can it find electrons? Well, we said, right, the double bond is a perfect place because the double bond is considered a region of high electron density. Okay, so this is a region of high electron density. The carbon-carbon double bond. All right. So this is what attracts electron deficient species. So if the bromine goes towards the double bond, what happens? Now the bromine contains a covalent bond, it's Br2, right? It's a diatomic molecule, that's covalent bond. So the shared electrons, right, they are not stationary, they're not still, they are not stationary, they are constantly moving. So why is there delta plus and delta minus? Remember we did this before. Delta plus means partial positive charge. Delta minus, partial negative. So why do these partial charges form? The partial charges are formed because the shared electrons are moving. As the Br2 moves closer to the double bond also has electrons. The electrons in the double bond starts to repel the shared electrons. And that's how you end up with delta plus, delta minus. Okay? So this is not a permanent polar covalent bond, all right? But these partial charges can develop as the Br2 moves closer to the double bond, is repelled by the electrons in the double bond. All right? So step 1 involves the double bond's electrons going towards bromine. The double bond's electrons go towards bromine. This is what this arrow shows. At the same time, the bromine-bromine covalent bond breaks. This is what this arrow shows. So what do you end up with? You end up with a situation whereby, oh, the double bond breaks, the bromine-bromine bond breaks. So you end up with this situation where there's a positive charge on carbon. There's a positive charge on carbon. Now this is called a carbocation ion. Carbon, positive ion. Carbocation ion. Okay. Now, obviously, the carbocation ion is not stable, right? Carbon wouldn't want to be positively charged. It doesn't have a fully filled outermost shell if it exists as a carbocation ion. So it will quickly accept electrons from any Br minus around and form a covalent bond with the Br, okay? And that's how you get the final product. Okay, so this is what we call electrophilic addition. Now, this is electrophilic addition of bromine on ethene. Ethene is easy because ethene is a straightforward example. But what if Mr. So were to now do electrophilic addition on this? Now, this is just one carbon more than ethene, it's propene, right? Propene is more complicated. Propene is slightly more complicated. Why? Why do I say propene is more complicated? All right, delta plus, delta minus. Okay, the electrons flow this way. Why do I say that propene is more complicated? Because if you notice, the plus charge of the carbocation ion can be at the end, like this, or the plus charge can be at the middle, like this. Right? And these two clearly are not exactly the same. Now, these are both carbocations. However, if you focus on where the plus charge is, the plus charge is not in the same place. Now, so these are given slightly different names. If you notice, this plus charge has one carbon next to it. This is called a primary carbocation. It's primary because there's one carbon atom next to the positive carbon. Whereas the one at the bottom has two carbon atoms next to it. So if it has two carbon atoms next to it, this is called a secondary carbocation. Because it has two carbon atoms next to the positive carbon. All right. Now there is an impact. Because where the positive charge is may end up forming different products. Now in this case, it won't form a different product because it's bromine. All right. But now we are going to move on to the third addition reaction where you will start to see that there will be a difference. Okay, so I hope you understand the concept of a primary versus a secondary carbocation. Okay. Okay, can I just check that everyone has copied this? On page 10. Okay, it's important the primary versus the secondary because very soon I'm going to go on to that next. Okay, we just did the mechanism of electrophilic addition of alkenes. So now I'm going to move on to the next part. Okay, to do the next part, we need to keep this in mind, the concept that there are two different carbocations possible, the primary carbocation as well as the secondary carbocation. All right. Okay, so let's move on to the third addition reaction. So now that we have learned carbocations, we know the mechanism of electrophilic addition. We are now going to apply our knowledge to the addition of steam. Now, when you add steam, now steam is basically H2O, right? Steam is what you get when you boil water. So it's H2O gas. So H2O looks like that. Then you realize, oh, it splits into H and OH. That means the covalent bond between H and O in H2O has broken. All right. Now, for this to occur, when you want to add steam to alkenes, you need a high temperature of 300 degrees Celsius, 60 atmosphere pressure, and H3PO4 phosphoric acid catalyst. All right. This is a complex situation now that requires you to use what you learned just now about carbocation. Quite clearly, propene plus H2O will form two different products. Why two different products? Because the H can be at the end, the OH can be in the middle. This is one product. Right? The H is at the end, the OH is at the carbon in the middle. This is one possibility. Or it could form this product, where the OH is at the end and the H is in the middle. And obviously, these two products are not the same. Right? Again, these are isomers of each other. Okay? If the OH is at the end, we call this propan 1-ol. If the OH is in the middle, we call this propan 2-ol. All right? So the first example already shows you that, okay, even though it's addition, there are two possibilities, two possible products, depending on where the OH is. Now, as Olympiad students, we should try to figure out which one is going to be the more possible, more common product. As it turns out, all right, the more common product in this case will actually be propan 2-ol. All right, so just let me share my screen again. The more common product is actually the propan 2-ol. This is what we call the major product. But why? So to understand and explain why propan 2-ol is formed in a larger amount, we need to go back to the carbocations that we just drew just now. All right. So just now we drew the mechanism for electrophilic addition. So if I may, can I just revise with you? The mechanism looks like this. You have the double bond. This is propene. Right? And then comes H2O, right? So what happens is that the double bond attracts the H. The covalent bond between H and O breaks. All right. Now this works because, of course, we have learned in covalent bonding, oxygen is more electronegative, so it's delta minus. The hydrogen is delta plus. So the delta plus is attracted to the electrons in the carbon-carbon double bond. So this, of course, leads to two different carbocations formed. The carbocation can either be, the plus charge can either be here, where you accepted the H here, maybe. Right? So this is one carbocation, or the plus charge is in the middle. Right? So we have seen two different carbocations. So the first one, remember, we called it the primary carbocation. How do you tell whether it's primary or not? You look at the positive charge. Where is it? Next to the positive charge got how many carbon? Here only got one carbon next to it. So next to it only got one carbon is called primary. So the second one at the bottom is called secondary carbocation, because it has two carbons next to the positive charge. Now, as it turns out, the secondary carbocation is more stable. A secondary carbocation with more carbons next to the positively charged carbon is always more stable. This is because carbon next to the positive carbon exerts what we call an electron donating effect. there are more carbons next to it to exert what we call electron donating effect. All right. So the more carbon atoms you have next to the positively charged carbon, the more electron donating effect there is. Remember, it must be directly next to it. So the primary one only has one carbon next to the positively charged carbon, not two, because the second carbon that's further away cannot exert much effect already. It must be directly next to the positively charged carbon. So because the secondary carbocation is more stable, this is the major product. So you think about it. Now the OH comes back. The OH has a minus charge. It will bond to the positively charged carbon. And that's why propan-2-ol is the major product. Okay, so for my Sec 4 students, I didn't explain this in class because I didn't go through electrophilic addition, the mechanism in class. All right, so this is new to you. So I hope you realize that because the mechanism is electrophilic addition, it involves the breaking of the carbon-carbon double bond. As a result of that, a positive charge will form, okay, in the intermediate of the reaction. This is called the carbocation. Whenever you have asymmetrical alkenes like propene, where the double bond is at a position that is not symmetrical, then you will have two different carbocations, the primary and the secondary carbocation. So because there's a difference in the stability of the primary versus the secondary carbocation, you will have different products formed. And in this case, propene prefers to form the secondary carbocation. Therefore, you will form more of it. So you have more propan-2-ol formed. Okay. So this is using addition reaction tree to demonstrate to you the differences in the carbocation. All right. So I know it's a lot to take in for the moment, but I hope you internalize it. All right. So can you just have a thumbs up once you have finished copying this, including the words? The words are important. Okay. Can? Now, this concept that the secondary carbocation is more stable is actually has a name to it. This rule is called, okay, this rule is called Markovnikov's rule. Okay, it's named after the scientist, a Russian scientist, Markovnikov's rule. So Markovnikov basically stated that, okay, whenever you have an asymmetric alkene like propene, all right, the hydrogen will always add to the carbon with more hydrogen originally. So in this case, you can see the hydrogen from H2O added to the carbon on the left-hand side. This carbon that I'm circling now. Because this carbon on the left-hand side originally already had two hydrogens on it. All right. So Markovnikov's rule basically ensures that the more stable carbocation is formed. All right. Now, finally, we're going to end off with addition reaction number 4, which is addition polymerization. This is how you form a polymer. Now, polymers are what we commonly call plastics. Plastic is called a polymer. All right. But plastic is a very layman word. Plastic just means it's a man-made material. Okay. So this is a man-made material, polyethylene. Polyethylene is made from ethene, obviously. All right. Polyethylene is what's used commonly to make plastic bags, Okay, the plastic bags you get from the supermarket, raincoats, all right, are all made from polyethylene because it's waterproof. All right, so how do you make this? You use high temperature and pressure and a catalyst. You cause ethene molecules to add to each other. So many small ethene molecules add to each other to form polyethylene. All right, Ken? So this requires a high temperature and a catalyst. All right, so you can see N molecules of ethene add to each other to form a very big molecule of polyethylene. So again, you notice that at first got double bond. In the polymer, no more double bonds. So the polymer doesn't have double bonds. All right, the polymer has no double bonds. So the polymer is saturated. Now, what is N? Why did we leave it as N? Why don't we just say 1 million, 1,000? The answer is because, the explanation is because N is not defined. N can be as small as 100, M can be as big as 1 million, depending on the duration that you left the polymerization reaction to run. And by varying the value of N, by varying the number of ethene molecules that are polymerized, you can change the chain length of the polymer. Generally, longer polymers are stronger. That's why, as an industry, if you are making a raincoat, for example, you would want the polymerization to be done for a longer period of time because raincoats need to be stronger than, say, a plastic bag because you have to wear, you have to put on a raincoat, right? Okay, so by varying the value of N, you can vary the strength of the polymer formed. Now, the way to draw the polymer is very easy. Okay, you just have to break the double bond, open left, open right. So let's see it now. Double bond is here. We break the double bond, open left, open right. Then we just keep the rest the same. Okay, then we put a bracket around it and put N. That's it. All right. Ken? Similarly, the next one is also the same. Break double bond, open left, open right. Put N. It's only the third one that's very problematic. Again, propene. Propene is always a little bit more complicated. Now, you notice that propene is asymmetrical. The way it's drawn is also asymmetrical, right? So the way to polymerize propene and visualize the polymer is you need to first redraw propene. So I always teach my students, always focus on where the double bond is, circle or box out the double bond, then redraw it. The double bond is here. What is attached to the carbon on the left? The carbon on the left has 2 hydrogens. The carbon on the right, though, has 1 hydrogen. Then something here, right? This massive thing here, we can just call it CH3. So this is also propene. This is how you redraw propene. And as a result of that, you just have to apply what I just said. The double bond breaks. Open left, open right. Open left, open right already. Then you attach the 4 things that's on the double bond. The HH on the left, the H on the right, and the CH3 on the right. And we just finish off with bracket N. All right. Now, all these have names. All these polymers have names. The one right at the bottom, this is propene. So propene becomes polypropene. Polypropene is the polymer used to make your water bottles. Most of your water bottles that you buy are made of polypropene. They started from propene, they did addition polymerization on it. Now, the second one, the middle one with all the 4 fluorines, this one is tetrafluoroethene. All right, so the polymer is called polytetrafluoroethene. But the more common name is its brand name. The brand name of the polymer is called Teflon. Teflon is the polymer used in non-stick coating on your pots and pans. So I'm sure you know you have done FCE before. Pots and pans, there's stick and non-stick. Non-stick pots and pans ensure that your food doesn't stick to it. All right. So Teflon is the polymer coating that's on the pots and pans. Finally, okay, this one, the first one is called polyvinyl chloride, otherwise known as PVC. PVC is a plastic polymer that's used to make pipes, raincoats, and so on. So polyvinyl chloride is an addition polymer, all right, that's commonly used to make pipes, raincoats, and so on. All right, okay? So this is a little introduction into an addition reaction where alkene molecules can add to each other. The double bond breaks, open left, open right, so it extends to form a very long polymer molecule. Okay? And this is what is commonly used to make what we call plastics around us. Now, the last page, page 13 of these notes, is just a quick summary comparing alkanes and alkenes. So I would encourage you to read that yourself. It's a quick summary of alkanes and alkenes. Now, our competition is on 23rd of May, which is next Tuesday. All right. So I would advise you to revise all the sets of notes you have been given so far, rewatch all the training videos, as well as to read your textbook. Reading your textbook, reading your notes really, really helps. All right. So that comes to the end of the training for Chemistry Olympiad. I'll stop the recording here. Thank you.